right. Good evening, everybody. I just got done with my appointment, so I'm going to wait here for just a minute. If you have any questions, come on in, and then I'm going to sort of show you my screen, and we're going to look at some questions that you are having some problems with for this chapter. Waiting for just a minute, getting things set up. Okay, so if you have questions, please stop in. Otherwise, I'm going to record some of these questions that you're having a little bit of difficulties. So in chapter 5, we're moving on to solving polynomials, polynomial equations. And the first section talks about factoring, so solving by factoring, which we've already done a little bit, and in behavior, which is important. So the first one that students were having a difficulties with was this one I have up right here. So we want to solve for z, and I have 8z squared minus 27. Now this can be factored, but it's a technique that nobody remembers. So this is actually a difference of cubes. So I can look at this as 2z cubed minus 3 cubed is equal to 0. And when I factor a difference of cubes, I think we actually went through this really early on in maybe the first office hours with the review material, but you do one of the first, so the 2z, I'm gonna make a line through my z so it doesn't look like a 2 itself, minus one of those 3's, and then you do the 2z squared plus. So it's going to be 2z times 3, that's a 6z, plus 3 squared, which is 9. So really, this is just a special formula you would have to memorize. It's that if you have something cubed minus something else cubed, then it factors out into an a minus b times a squared plus ab plus b squared. So I factored this out, and I can go ahead, and when I factor things out, I can set each factor equal to 0. What we're going to find in this section is you don't always have to go down to linear factors. Once you get a quadratic, you can actually just use the quadratic formula for this. Why not? We already know that, right? So if I set each one of these equal to 0, I would have 2z minus 3 is equal to 0, which means 2z is equal, or z is equal to 3 halves. So that's going to be one of my zeros. My other two, this actually doesn't factor, so I can use the quadratic formula. I'm going to say z, or my x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. So this is something that you're going to have to know, memorize, take to your grave. All right, so I'm going to plug things in. So b is a 6, so I have negative 6 plus or minus the square root of 6 squared, which is 36, minus 4 times a times c. All right, so I plug in the 4 and the 9, all over 2 times a, and my a is just 4 there. So I'm going to simplify this out. I have z is equal to negative plus or minus, so 36 minus 4 times 9. Well, I have a calculator here, so I'm just going to do that to figure it out. I get negative 108. So the square root of negative 108 divided by 2 times 4, which is 8. Now, negative 108, you see there's a negative there, so the square root of negative 1 is going to be an I. So this is going to be an imaginary number. but we need to include those in our solutions. Square root of 108, that's actually a perfect square of 36 times 3. So what I can do is I can pull out the square root of 36, which is 6, and then only square root of 3 will be left. So that second part over here, when I break it apart, it's going to be negative 6 plus or minus I square root of 3 all over 8. So there's 2 more answers here. The last thing I could do with it if I want to is I could actually cancel out the 6 and the 8. So probably my final answer would be negative 3 over 4 plus or minus 3i root 3 over 4. So that last step, I would cancel those 6's out. Now make sure to cancel out from both terms, but there would be my 3 answers there. Okay, so that's a factoring one. So what else do we have with section 3.1 or 5.1 with polynomials? We talked about end behavior. And so the idea behind end behavior is, you know, polynomials are very smooth, they're continuous, they bend, they turn, and they go to either infinity or negative infinity at the ends. And that's what we call the end behavior. How do we figure out end behavior? It really basically boils down to 2 things. So here we want to describe the behavior of the graph as x goes to plus or minus infinity. So that's what we call the end behavior, because when x goes to plus infinity, we're going to the right side of the graph. And when x goes to negative infinity, we're looking at the left-hand side of the graph. So in this problem here, I told you it boiled down to 2 things, right? So it boils down to the leading coefficient. That's going to be the number in front of the highest power of x, and the degree is the highest power of x. So if I multiplied all this out, I would get a polynomial with 4 terms, most likely, and the highest power would be an x to the 4th. I can use a shortcut with this if I'm just looking for the end behavior. I notice here that for each factor, the highest power here is x squared. The highest power of x here is just x, and same here with x. It sort of looks like a 7 times 1 times 1, x to the squared plus 1 plus another 1, x to the 4th. So this has an even degree, and it has a positive leading coefficient. So what I want to think about is, hey, what other kind of graph has an even degree that I know, a polynomial graph that has an even degree and a positive leading coefficient? Well, it's that parabola. So parabolas go up to infinity on both sides. So if my degree here is even and my leading coefficient is positive, then on both sides for the end behavior, that function q of x is going to go to infinity. It's going to go up, up, and away. And I know from factoring this that my other zeros are at actually 0. So I could sort of fill this in a little bit. It's going to touch here at 0. There's going to be another 0 here at 4. I get that from this factor here. And another 0 at 8. And the way I would get those is just through looking at factoring it. So that would be another 0 there. And then it would go up like this. That's what the graph would look like. But in general, when you have the leading coefficient and the degree, there's essentially 4 cases for the end behavior. And I'll go over those really briefly. Just sort of pictorially. So if my degree over here can either be even, like we just saw, or it can be odd. And my leading coefficient, I'll just say leading coefficient, LC, that would either be positive, like this one is, or negative. So I have an even coefficients, my end behavior goes up to infinity at the ends. If I have an even coefficient with a negative leading coefficient, so an even degree leading coefficient that's negative, it's like a parabola that's been flipped. So it goes down to negative infinity on both sides. So I would just put in a negative infinity for these two, if that was the case. Now an odd degree looks like, you know, x to the first, that's a line. So really with odd degree, we think about slope. So if I have something with a positive slope, hey, it's gonna go down to the left. So it goes to negative infinity as x goes to negative infinity. So to the left, it goes down, but to the right, it has positive slope. So it goes up to positive infinity. If I have a negative coefficient, well, the slope is going down. So it's going to go up to infinity on the left-hand side and then down to negative infinity on the right-hand side. So with an odd degree, it's going to go up on one side and down on the other. With an even degree, it either goes up on both sides or down on both sides. So I hope that that helps you out. All right. So when we look into the next section, we're talking about synthetic division. And this, yeah, this is a tough one. I did make a video about this one, but let's go ahead and take a look at the idea behind synthetic division. Synthetic division is a pretty interesting concept, but it's just like dividing, but we're going to do it without listing all those x terms. Now this one is more difficult because we do have imaginary numbers, right? So synthetic division only works when you are dividing by a linear term. So I have to be dividing by just a linear factor, x plus or minus something. And what I do is first is look for the 0 that I would get out of that. So if I have x minus 2i, my 0 would be x is equal to 2i. So this is how I set things up. I have 2i, my 0 there, that's going to be what I'm dividing by. And then I take all these coefficients and I have to go from highest degree to lowest degree. And I put them all up here. So I have my x cubed, which is a 3. I have my x squared, which is a negative 10i. I have my x, which is a 6. And I have my constant term without any x's, that's a 6 minus 2i. So again, this is more difficult because it has imaginary numbers. So now, really when I divide things, if I divided things by long division, it would be a series of multiplications and subtractions. And that's going to be the same case here. But when I subtract, I sort of add by the opposite thing. So that's, you're going to see the sort of same process going on here. So what I'm going to do is I'm going to bring down, I'm going to look at that x cubed term, the 3. And remember, long division is a series of multiplications and subtractions. So here we're going to multiply that 3 times the 2i. We get 6i. Now instead of subtracting here, we're going to add. So we add negative 10i and 6i, we get negative 4i. I'm going to go ahead and take this negative 4i times the 2i again. That gives me negative 8i squared. But I squared is negative 1. So negative 8 times negative 1 is 8. I'm going to add these two and I'll get a 14. So 14 times 2i will give me 28i. And when I add these, I get 6 plus 26i. All right, so this is these coefficients that I get. So when I divide this factor, x minus 2i, by this polynomial, these coefficients that come down here, these are actually going to be 1 less than the ones they were up here. So instead of an x cubed, this is an x squared. Instead of an x, this is going to be, I'm sorry, instead of an x squared, this is going to be an x. Instead of an x here, this is just going to be plus 14. And this is our remainder here. So what we have over here is our remainder. And if that remainder is 0, what that meant is 2i is a 0. Well, it's not in this case. So when we have a remainder, we can factor this out and we add that remainder over that original divisor, which was x minus 2i. So another way to express this division up here would be by that polynomial plus the remainder over the divisor. it's a little bit, I mean, this example is complicated, so I can see why you missed it. But this will actually help us when we're trying to find zeros. Okay. So let's see what else. So moving through section 5.2. Okay, so now we're actually finding zeros. So one really good tool that we have to find zeros with is called the rational zero theorem. So there are a lot of different things that we can use to find zeros. We can factor if that's a possibility. You could probably do grouping on this one, but I just want to show you the other possibilities, because probably on the final, probably on a lot of these questions, you won't be able to factor. You'd have to use this division process. So there are two other things that, with the advent of the calculator, the nice trusty calculator, we don't really need to use anymore. Those are the bounds on the zeros and Descartes' rule of signs. They're good things to know, but again, the calculator can help us out here. But the first thing we want to do is sort of figure out what are the possible zeros here. So there's actually a rational zero theorem. It says if I can have a zero of this polynomial, where I can write it as an integer over another integer, like a fraction, then it's going to be of this form. And you'll see it in your homework as maybe the P over Q theorem. So I take the factors of my constant term. They call that Q. And I divide it by the factors of my linear. Not linear. Let me scratch that. By my leading coefficient. You've used that word before. By my leading coefficient, by the factors of my leading coefficient. So actually, I think the constant term they call the P, and the leading coefficient term, which would be 1 in this case, that 1x cubed they call the Q. So mind your P's and Q's. If you take all the factors of P and divide them by Q, those factors, you'll get all the possibilities. Now they won't all work. In fact, none of them may work, but it's a good place to start. So if I'm looking at my factors of P over here, the constant term, 64. So factors of 64 would be 1 and 64. 2 goes into 64 because it's even, 32. 3 does not go into 64, but 4 does. 4 times 16, that works. 5 doesn't, because it doesn't end in 5 or 0. 6 doesn't, 6, because 3 doesn't go into it. 7 doesn't, 8 does, and it's really 8 times 8. So these are all the factors of P, of that constant term. Now I'm going to divide those by my leading coefficient. Well, thank goodness there's only 1 there. So the only factor of 1 is 1. And then these can be plus or minus these. So all the possible zeros are in this list. But I mean, you can note that if you take all plus and minus combinations of here, we have 1, 2, 3, 4, 5, 6, 7, and double that. So we have 14 possibilities. That's still a lot, right? So now what you can do is you can actually use your calculator to help figure out where these will be. So I'm going to plug this into my calculator, and I did make a pretty good video about this, which goes through the process of what you can do here. So I'm going to plug in x cubed plus 4x squared, and it's okay to use calculators on your test, as long as they're the approved ones. So the TI calculators are fine. I'm going to graph it. And I'm going to have to zoom on my calculator. Come on, calculator. So if you did something like this on your test, just say you used your calculator, and what do I want? I want zoom standard. There it is. And when you look at the graph here, Okay. I see that it crosses once, and it looks like it to me it crosses at -4. So give you a little look-see here. Whoa, that's very too close. It's not going to be able to look at it. Oh, there we go. So it does look to me like it crosses at -4. So what I'm going to do is I'm going to take that -4 and I'm going to take that -4 and divide into it. If it works, then I'll be able to use the rest of the polynomial because I can use the quadratic formula. So I'm going to clear this out and show you what I do. Okay. So I take this polynomial and I'm going to write down the coefficients because I'm going to be using that synthetic division. So I'm writing down the coefficients in order, and I saw that -4 goes into it. So I'm going to go ahead and synthetically divide by that -4. I bring down 1, multiply -4 gives me 0, or gives me 0 when I add it to 4. -4 times 0 is 0. I add, I get 16. 16 times -4 is -64. And I add and I get 0. That's my remainder. So yeah, so since my remainder is 0, it works. Yay. So now I know that x equals -4. That's a 0. But what I also know is that 1x squared plus 0x plus 16 is another factor of the polynomial. So what I have, I've factored this into x plus 4 because that's the factor that would give me x is equal to -4. And then I have x squared plus 16 is equal to 0. So I up through synthetic division. And when I get down to a quadratic, I can use quadratic formula. In fact, I don't even have to use that here. I can use the square root method. So if I say x squared plus 16 is equal to 0, I have x squared is equal to -16. And as long as I know to take a plus or minus when I take a square root of a number, I have x is equal to plus or minus -16, which gives me plus or minus square root of -1 is an I, and 16 is 4. So I have these three zeros. I have plus or minus 4i. I have -4. And that -4 would just come from this. So those are three zeros. Hey, you may have noticed something from these exercises we've been doing. If you look at the degree of the polynomial, 3, that actually gives you the exact number of zeros. You'll learn that in section 5.4. So you can figure out how many zeros there should be, and you can use this rational zero theorem to divide in the correct ones, and that will factor the polynomial for you. Okay. Let's go to the next one. Okay. So I think we are in section 5.4 now. 5.3 maybe too. So here we have a polynomial and it's factored. So we want to find the x-intercepts at which f crosses the axis and express the intercepts as ordered pairs. So here's where we can put everything together. So once you get to this point, you should know exactly what you're doing. So probably to get to this point, you would have had to factor this polynomial by using synthetic division. We would have looked for the end behavior. So we can actually graph this one. It'll be pretty easy. Okay, look at this. If I was looking at the end behavior, my leading coefficient would be an x squared, so I have to square this x, times an x cubed. So I have to cube that times an x. That gives me x to the 2 plus 3 plus 1, that's x to the 6. So there should be 6 zeros there. Leading coefficient is going to be the 1. So the degree is equal to 6, that highest power. The leading coefficient, it's all 1 squared, 1 cubed, and 1. all this together, it's just 1. So remember, even degree, like a parabola, leading coefficient opens upward, so it's going to look like this on the ends. That's the end behavior. It's going to go to infinity on both the left and the right. So what we can do now is we can actually plot these zeros. Now this is going to be a sort of cool part. So I know from this graph, let me just, let's see, let's erase this here, because we already talked about that. From this factored polynomial, I see that we get a 0, -1, a 0 of 4, and a 0 of 3. But hey, I promised you 6. I promised you 6 zeros. That's what the theorem says here. So let's go ahead and plot those. So here's the one at -1, 0. Here's the one over here at 1, 2, 3, 0. And here's the one over here at 4, 0. So how do I account for those other zeros? Well, if you look at the powers here, see this squared? What that would mean is that x equals -1 actually occurs twice. So I have to count it twice. X equals -1 is what we call a 0 of multiplicity 2. I look at x equals 4. Wow, there's 3 of those. So x equals 4, I have to count 3 times. So of course we call this a 0 of multiplicity 3. And there's only a 1 in this, so this is a regular 0. But if you count 2 for the first one and 3 for the second one, that's 5, plus the third one is 6. So when zeros have multiplicity, interesting things sort of happen. If my 0 has a multiplicity that is odd, it actually will go through the graph just like a line. So notice that over here where x is equal to 3, that's just a multiplicity 1. So look at that one just yet. But if I have a 0 of multiplicity 2, that's going to be even. It's going to look like a parabola right there where we have the 0. It's going to bounce off the graph. So this one over here with multiplicity 2, it's going to bounce off the graph. So by my end behavior, I can look at the whole picture without graphing it. I know that it's going to go down here, and since it's even multiplicity, it's going to bounce off like. And I know over at this side, it is going to go up again to infinity because of the end behavior. Okay, so that's going to bounce off like a parabola. The 0 at 3 doesn't have any power on it. So when we get to 3, it's going to do just like a line. So it passes through smoothly, just like a line. Notice this 0 at x is equal to 4. Well, it has an odd degree, so it's going to pass through, but it's going to flatten out a little bit like a cubic. So at this 4, it sort of flattens out and goes up like that. You can see the little turn in the graph if you were to plot it. Okay, so this one says, at what x-intercepts is it cross the axis? So your answers would be at 3, 0 and at 4, 0. Those would be the two where it crosses the axis. Since the -1 had multiplicity 2 and even multiplicity, it bounced off. All right, so when you get to this point, you'll be able to put everything together there. All right. Intermediate value theorem, it's actually a pretty easy theorem. It's intuitive, but it's a theorem, it's mathematical, so students have a hard time digesting it. Basically, the intermediate value theorem says, if you have 2 points for a polynomial only, so this only works with polynomials because they're continuous, they don't have any breaks in it. If you have 2 points for a polynomial, and if you take the function at those 2 points, so if I take the function at 3 and the function at 4, if those two signs are different, then there has to be at least 1 0 in between 3 and 4. So all I would have to do is plug these two values in for the function. So I would have 3 cubed, that's 27, minus 5 times 3 squared. That's like 9 times 45. 45, 27 minus 45, 27 minus 45. Negative 27. Oh wait, negative 7. Negative 17 plus 24. That's going to be a positive 7. Minus 8. Whoa, okay, so positive 7 minus 8. That should be negative 1. All right, I'm going to do the same thing here, but I'm going to use my calculator because that was a little scary for me. Okay. But if these two differ in sign, that should be a 4 that I plug in, then I know that there's at least 1 0 in here. So I plug it into my calculator. 3, whoops, 4, I meant 4. 4 cubed minus 5 times 4 squared plus 8 times 4, and then minus 8. All right, I get an 8 there, and now I'm just gonna verify the first one because I tend to make mistakes, but we'll hope that I don't. But let's just verify it here. All right, I get, okay, I was off a little bit. This is actually a minus 2 according to my calculator, but it does change sign. So what that essentially means is graphically, over here at 3, we have a negative 2. So I'm down here. But when we jump to 4, this goes up to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what that means is somewhere between 3 and 4, where x is equal to 3 and 4 here, this has to go through and there has to be a 0 there. That's all the intermediate value theorem says. So this one would be yes, there is, because those two differ in sign. Okay, only works for polynomials though. But we're dealing with polynomials now. So this can help you narrow down where a 0 would be. So if you had that long list of zeros and they had fractions in them, you could sort of evaluate it at 2 points, or you could look at it on your calculator and say, hey, there's a 0 here, so I'm going to test that one for synthetic division. Okay. All right. So this last one's a difficult one, and you would have to use synthetic division here, but here's the kicker. When you have a 0, what I call a complex 0, there's a theorem that says that the conjugate, so what's the conjugate of an imaginary number? We sometimes say it's x bar. It's going to be the number, but we put the opposite sign in front of the imaginary part. So that number and its conjugate will both be zeros. So notice this is a degree 4 polynomial. So I would have 2 zeros there that if I'm given 1 and it has an imaginary part, its conjugate has to be there. It's a theorem. So what I would have to do is multiply those together and divide, but here's the kicker. I can't do synthetic division. I have to do long division. All right. I did make a video for something like this because students miss it all the time. It's a difficult problem. So please check in Canvas for that video in section 5.4. I'm giving you the idea right here. It will help you out quite a bit. All right. Well, no one stopped in tonight, but that's okay. Hopefully, if you're having problems, you'll come back and video out. All right. Have a nice night.